Okay, great. Then let's get started. So, hi everyone. My name is Naeem Darguth. I'm a researcher in the Electricity Markets and Policy Department here at Berkeley Lab. Welcome to the webinar, where my colleagues and I are going to be discussing an idea that we've been kind of thinking about for some time, which is Berkeley Lab Solar Data Commons. And we're going to be presenting our various solar-related data sets and data sharing. So note that the webinar is being recorded and we will be posting the webinar online. We have a lot to cover today, so let's get right into it. So a quick agenda. After a quick intro to provide context for the webinar, we're going to dive into the principal data sets, so tracking the sun, utility scale solar, our solar to grid data, our wholesale electricity market data, and interconnection queues data. Each of these are going to be presented by different lead researchers on the Berkeley Lab team. Myself for tracking the sun and demographics, Joachim Seal for USS, or utility scale solar and solar to grid, Dev Milstein for the wholesale market data, Joe Rand for interconnection queues. And then we've invited Ken Gillingham, who's a professor at Yale University, and with whom we've collaborated on a number of projects in the last decade or so to discuss some of our collaborations and the data used there. If you have any questions during the webinar, please use the Q&A feature in Zoom at any point. No need to wait till the end of the webinar. And we'll be sending a copy of the presentation to everyone on this call, as well as hosting it on our website. So don't worry about noting down all the website links that you'll see on the slides. So as you may know, as part of the Solar Energy Technology Office funded research and analysis, our team in the Electricity Markets and Policy Department here at Berkeley Lab puts a fair amount of effort in putting together, in cleaning, managing, and curating a number of unique data sets. And in addition to using these data sets in our own research, we'd like to find ways to kind of expand the tent and really make this data available to others as well. When possible, we already try and share as much of the data directly on our website, emp.lbl.gov. However, in a number of cases, some of that data is protected by non-disclosure agreements and we aren't able to share directly. In those cases, we try and share online data visualizations that enable customized analysis of that confidential data through maps, charts, and graphics. And we also try and share data at an aggregated level, kind of obfuscating any personally identifiable information. So the objectives of this data commons is really to make our solar-related data as accessible as possible. And I should note here that though the focus is solar, it is relevant beyond solar because there's a lot of parallels with our work in wind. And we actually are going to be talking about some of this data today that's beyond solar. And so Joe and Dev, for example, will be presenting some similar data sets. So the objective today for the webinar is to describe the data we manage, including what can be shared directly and the tools we've developed to help others interact with the data. So let's begin with the distributed solar data, which includes our tracking the sun and solar adopter income and demographics data set. The landing pages are linked here. So the tracking the sun data is composed of individual system level data with a focus on distributed solar, mostly systems that are smaller than 5 megawatts AC. We get this data from over 63 state agencies, utilities, and other organizations that are related to incentives, interconnection, or net metering. In some cases, the data is fully public and available, but in others, we get additional data or all of the data, in some cases, through non-disclosure agreements. Our full sample in the upcoming Tracking the Sun is 2.5 million systems through 2021, and that represents almost 80% of the entire US market. At the very minimum, we have installation date, zip code, system size for each of these systems, but in most cases, we have much more information on each of these systems, a total of 80 fields we are able to kind of put together. All the data, which comes in various states of messiness, is going to be standardized, it's cleaned, and then appended with additional data from spec sheets, for example, from the equipment manufacturers. So now on to sharing of this data. All the system level data from Tracking the Sun that we can share, we already do so in a public data file that can be downloaded on our website. This is data that we're allowed to share because it's not protected by NDAs. We update this once a year, usually at the same time as a report. Note that no addresses are included for any of the systems. We do have a visualization that makes use of the full data sample and really enables users to develop customizable maps and figures. You can find the visualization by just going to this link here. And I'm going to just quickly show you what that looks like. So by going to the Tracking the Sun landing page, you can access this by clicking on Visualizations and the Tracking the Sun tool. And here, you'll see some information about the tool, a user guide that you can download, and you can do some customized analysis for specific states and recreate some of the figures that are in the report for specific states. So if we were interested in Arizona, we could look at size or characteristics, systems with battery storage, some market characteristics, percentage of third-party ownership, etc. So we have a number of these charts that are customized for the state that you're looking at. You can also compare by customer segment instead. And then you can also select several states if you're looking to compare states. So for example, the national, Arizona and Colorado, you can kind of understand the installed price distributions or other distributions here in selecting a range of years. So let's go back to the slides. So we aren't able to share addresses for any of the programs, but we are working to be able to share aggregated data, at least at the US Census tract level, which is an area that includes maybe a few thousand households usually. We already have approval to share California census tract information from the CPUC, and we're working with our lawyers and to modify the non-disclosure agreements to be able to share from many more states. Now, we augment the Tracking the Sun data with a number of other data sets that increase our distributed solar market coverage. We use 2 data service providers to really increase the number of PV systems in our overall distributed solar data set. There's BuildZoom, which provides solar addresses and installation date proxies that are extracted from permitting data, which is collected from municipalities. This, in the last version of the report, expanded our coverage to 44 states with an additional 233,000 systems. The second data provider is Ohm Analytics, which also mines permitting data, but has specific solar focus, so they're really able to extract a few more fields than in BuildZoom. This increased our coverage in 16 of the states, with another 170,000 systems in the last version of the report. The next data set we pull from is Experian, which is known as one of the 3 big credit bureaus. Experian doesn't provide us with solar data per se, but they are able to provide household income estimates and other demographic data for all the addresses we provide them. And so this allows us to bring income and demographic information to the PV adopter data and merge these. And this is quite unique as far as we know, as usually researchers kind of depend on US census level data, whereas this is household specific. The final data set we pull from is CoreLogic, which provides real estate characteristics of properties where residential solar is installed. Though we can't share a data dictionary that shows the details of what fields are available, we can share a general description of the data. If you get in touch with us, we can do that. So now we use those kind of last data sets that I described in the previous slide in combination with Tracking the Sun to develop a solar adopter income trends, data, and visualizations product that we report each year and update each year. In this, we describe the trends for residential solar adopters over time in various geographies in this annual tracking report. We're still developing that report that goes through 2021, so installed systems through 2021, but we do hope to release it in the coming months. Since a lot of this data is protected by NDAs, what we've done is create an online visualization tool that kind of allows a user to interact with the data, creating custom maps similar to what we saw in the Tracking the Sun tool with user-specified geographies and income thresholds. And I should note that though we don't kind of share the underlying income data, we do share data aggregated at the US Census tract level. The report and visualization can be accessed through a single web page, the solardemographics.lbl.gov, which I can show you how to access here. So from the Solar Demographics landing page, which is that link I just shared, you can click on visualizations and again on the tool. And here you have a similar structure to what we had seen before, except that you have a kind of a mapping, which you can click and zoom as you would in Google Maps, and then create custom distributions of incomes of solar adopters, for example. So you can look at the distribution of solar adopters for a specific state. So looking at New York, for example, the distribution, and then you can also click on time trends to understand how those income distributions have changed over time. There are a number of income metrics, map thresholds, as well as geographic level that you can change going from national, state, all the way down to county. There is a document that you can, that describes the features, and there's also a small video that kind of walks through how to use the tool. As I had mentioned, you can download any of the maps here, but especially the tract level data that contains all the data at the tract level. So now let me go back to my slides. So now that I've presented this, I'm going to turn it over to Yo, who's going to be going through the utility scale solar data.
Yeah, thank you, Naeem, very much for this nice introduction. My name is Yo Seal. I'm a Senior Scientific Engineering Associate at Lawrence Berkeley National Lab, and I work primarily on utility scale solar data. We have an annual data and market report on utility scale solar that has been around for nearly 10 years now. That I'm going to dive deeper into. You can find much more information about the project at utilityscalesolar.lbl.gov. Next slide, please. So this is a nice companion report to the Tracking the Sun data that Naeem just represented, which focuses, his Tracking the Sun data focused primarily on distributed PV. The utility scale solar project focuses instead on large scale installations that are larger than 5 megawatts AC. Throughout the entire continental United States, including Hawaii and Alaska, although in Alaska we don't really have any projects yet, that are ground mounted. So we don't look at rooftop or carport installations, but ground mounted projects that are larger than 5 megawatts. And we use both publicly available data that exists and is collected by various kinds of public agencies, as well as private data that we get from interviews and existing relationships with solar project developers and project owners. And what really the primary value add is that we do here is that we bring together and synthesize all this data that exists in the utility space and harmonize it and really augment it. There are many different ways how one can report the data. It's not always obvious how one should link information pertaining to specific projects because they don't have, for example, consistent project IDs. And so that is a lot where we spend a lot of time and attention on. And then we also create additional derivative metrics that may be more easily understandable. For example, performance metrics such as capacity factors, so where you can see how performance have varied over time, both between projects or within a project. As I said, we use both public data, and here we draw from information from the Energy Information Administration, or EIA, and the various forms. Key here is, for example, the 860 dataset, both the monthly and the annual data, but also generation reports, for example, the EIA 923 form, as well as forms published by the Federal Energy Regulatory Commission, FERC, for example, the FERC Form 1 that utilities need to file, or FERC Form 556 for qualifying facilities. These are projects that try to get the QF status and have to disclose project level technical characteristics as well. So we try to bring all this together. I'm not going to go here through each of these individual points in the interest of time. That we collect metadata for each project, technical characteristics. Does it have tracking, or is it a fixed tilt installation? What kind of modules does it use? What is the megawatt AC capacity? In DC, what's the capacity? Does it have storage? If so, what's the size of the storage? What's the duration of the storage? Who's the developer? Who's the owner? What is the geolocation of this project? What is the solar irradiance at that project? What were the CapEx costs? What was the performance of this project? What is the power purchase agreement price of this project? We use some of the information about CapEx and OpEx to calculate levelized cost of energy. So what is kind of the average cost to generate electricity with this project? And finally, how does that then compare to the wholesale market value? If all of the generation would be sold at the nearest node at coincident wholesale energy prices, or if the capacity would be bid into capacity markets, what would be the revenue that a solar developer or solar owner would get from that? And how does that then compare to both the levelized cost of electricity and the PPA prices? And how has it varied over time with increasing penetration, etc.? Next slide, please. So in terms of the data coverage, I have shown here on the right in a map of the continental United States and Hawaii, where we have all of our projects that are larger than 5 megawatts AC. In gray are existing projects, and dark blue are new projects that were just installed in the year 2021. At least compared with the EIA data, we have 100% coverage of the metadata of the plants. For CapEx, we have about 90% coverage, roughly the same for levelized cost of energy. Capacity factor, we have nearly complete coverage. OpEx is a little more difficult to get because only investor-owned utilities need to file that kind of information for projects that they own themselves. And given that they only comprise about 10% of the total market of all utility scale solar projects, we only have OpEx for that set of projects. PPA prices, we have about half of the market. Some plants just don't have PPAs because they are merchant projects, or they do not have to report to FERC because they are not under FERC jurisdiction, such as ERCOT. Or they are really in the business-to-business segment with corporate entities and not utilities, and so don't have virtual PPAs that are a little bit more difficult to track. I'll leave it at that here, just to reiterate, if there are potentially solar developers or owners out here attending this webinar and you'd like to contribute to this data set, we always look for data collaboration, and in general only disclose confidential data in an aggregated manner so that confidentiality is still maintained. Next slide, please. So about data sharing, we primarily share most of the underlying data as long as it is not governed by a non-disclosure agreement on our project website that you can find at utilityscalesolar.lbl.gov. And there at the bottom of the site, you can find an Excel workbook that has more than 40 tabs. And for each of the individual graphs that we report in our briefing slide set, so we have about 60 slides or so, and each of the graphs that is discussed there, you can find all the underlying data that is used in the graphs. So that is usually summary data or aggregated data, as well as project level details on one of those tabs as well. And you can find all of that. One set of data that is not shared there is CapEx data that we get from the Energy Information Administration under non-disclosure agreement. And so we have near complete CapEx coverage, which I think is very unique. I'm not really aware of any other entity out there that has access to this data. And we only report summary data from that. We also have on our website data visualizations, where you can find a little writer that is called visualizations, and click on that to find 6 interactive Tableau visualizations there. That discusses both deployment trends and technology trends of each individual project, as well as capacity and generation over time by project and by state. You can find CapEx, LCOE, and PPA prices over time, either by region or by plant, and you can find capacity factor data. There was a question of where do we actually, show this public data file. There's another little tab on the website that's called Files, and if you click on that, you can download that Excel workbook there. We are very happy to entertain specific requests to share data that is not already in the Excel book, and just shoot me an email if you have any requests there, and we'll see what we can do for you. If you have any data that you would like to contribute, we are always very open to that, and would love that. Next slide, please. So I'd now like to back up a little bit and talk about another 3-year-long project that had wrapped up last year, and that is continued in part, at least, in this utility scale solar data series that I just presented about. This project that wrapped up was called Solar to Grid, and it investigated the system impacts, reliability contributions, and the market value of solar generation in the United States. And it included both large-scale projects, and that is the portion that will live on in the utility-scale solar data series, but also distributed solar. And that, unfortunately, is an aspect that we will, at least at the moment, not continue. Next slide, please. So on the project website that was just shown there, you can download a lot of data, and I'm going to speak about that in just a second. But to back up, the purpose of this project was that we really tried to get all of the large-scale projects that is reported in EIA 860. So those are all solar projects that are larger than 1 megawatt, as well as distributed PV, and we get capacity here from the form EIA 861. We looked at all the solar that was deployed in the 7 organized wholesale markets, or ISOs, RTOs, as well as 10 additional balancing areas that had the most solar deployment. And we looked at a time period from 2012 through 2020. And you can see at the bottom right, there's a map that shows the 7 ISOs and then some of those additional balancing areas, for example, Arizona Public Service or FPL in Florida. The focus here was really on standalone solar, given that at that time, at least, we did not have a lot of solar hybrids deployed yet. What we did was we created hourly, either project level for utility scale projects or county level for distributed PV, generation estimates that were based on plant-specific technical characteristics, as well as local weather data that we get from the National Solar Radiation Database, which we then debiased in a step that used both hourly isogeneration reports, as well as monthly or annual generation records for each specific project that we got from EIA 923. For the region of Texas or ERCOT, we were also able to use empirical hourly reports of the 60-day reports, which we could use to see what the generation was and also infer curtailment rates. We used then the capacity credit or developed a tool to estimate the capacity credit of solar. What is the contribution of solar to reliability requirements, and developed either plant or county level estimates based on the prevalent rules of an ISO. And for regions outside of ISOs in the balancing areas, we just looked at what the contribution is during the top 100 net load hours. And finally, we then use this, both the capacity credit information and the hourly profiles to estimate what the wholesale market value is based on nearest hourly LMP prices that Deb will talk about in just a second, as well as zonal or seasonal capacity prices. And that is shown over here on the map, and you can kind of see how it varies both between regions. In Kaiser, it's kind of lower than Florida, for example, but also within regions. So for example, in Western Texas, there are transmission constraints. Because of that, some of the values for solar projects that are behind those transmission constraints is lower than elsewhere. Next slide, please. We publish all of the annual summaries of this data, either on a plant level or county level, on our website. And so that includes generation, curtailment, energy value, capacity credit, capacity value, and a value factor that compares the value of solar against that of a flat block of power. You can download that on the project website. And we also then, in addition to these annual summaries, report hourly either plant or county level data. And I think that is a very unique data set that does not really exist elsewhere much, I think. It's a fairly big data set, so we didn't host that on our website ourselves, but have a link to the Open Energy Data Initiative, and you can find the data there and can download it there. In addition to that, we have visualizations. I think in the interest of time, I may skip that because we're running a little late, but you can go to our website and then click on the right of visualizations, and then find one for regional annual capacity and generation summaries by sector, and another one that is a map where you can then look at plant level energy and capacity value for utility scale solar projects, both by year, so you can see kind of how it has varied over the year for each project, but also then aggregated on a balancing area, ISO level, or on a state level. And those kind of visualizations will carry over to the utility scale solar data series. This year, we're currently working on an update of this data, and we'll probably publish that in September. Yeah, thank you very much for your attention. If you have any further questions about our wholesale market valuation work or the utility scale solar data series, please feel free to contact me. Thank you.
Hello, everyone. I'm Deb Milstein. I'll talk about our wholesale market electricity price data today. Next slide. So we use wholesale market price data for the lot of activities that Yo just spoke about. In general, we use it to help estimate the empirical market value of wind, solar, and hybrid generation. And we also use this data to look at how the deployment of wind and solar and increasing penetration of wind and solar into electricity markets affects market value in general, system value, and the need for different infrastructure development, such as transmission. In terms of energy prices, we collect prices at market nodes. There's about 50,000 nodes across the 7 major ISOs and the energy imbalance markets in the US. We collect data on real-time and day-ahead prices. It's hourly. Some of the ISOs have sub-hourly prices, and we primarily look at hourly. In a subset of nodes, and many of the nodes actually, the real-time prices can be broken into different components that include energy, losses, and congestion. And in Texas, we also collect something called the operating reserve demand curve prices. And these are prices that are added to wholesale real-time prices as a way to incentivize additional investment in capacity resources. So Texas doesn't have a separate capacity market, and this sort of serves that purpose. We also collect capacity prices where there are separate capacity markets in the other ISOs, either as reported by the ISOs themselves or sometimes from other sources, such as from Berkeley. So that is the set of prices we collect. Next slide. And so with that, we use those prices in many of the analysis we were just talking about, but we also developed a tool to look at the prices more directly and look at some of the relationships between prices and renewable energy. This tool is called the REWEP tool, or the Renewables and Wholesale Electricity Prices tool. You can see the link on the screen, and I will chat it to everybody as well. Let's see. So a couple examples of what the tool can do on the right here. There's a mapping function which shows characteristics of nodal prices across the country where they're available. And for example, this characteristic we're looking at in the top right panel here shows the negative pricing frequency from 2020. So that shows that many nodes, especially in sort of wind-heavy area near Oklahoma and Kansas, have had a high frequency of negative prices in recent years. So that's up to like 20%. And another function we have added this year to this tool is this sort of 360 by 24-hour average price. So there's the top panel in the bottom figure here shows hourly prices for each hour of the year for all of the ISO nodes, I think including the energy imbalance area. So the average hourly price each hour. And so, one thing that's interesting in that is you can see how the daylight hours are represented by that sort of darker blue shade that you can see going across the center of that period. And that shows that prices are lower during high solar hours, basically. And the bottom panel there is for ERCOT, and that's a pretty different characteristic there. You don't see the sort of solar depression. Prices midday because there's not as much solar penetration yet. And you can see the effect of the extreme weather in 2021 in February is quite noticeable there, with prices getting up to thousands of dollars per megawatt hour for a prolonged period of time. We use these types of prices and analyze their links to system impacts and to renewables, including solar and wind, in a number of reports, which some of them are linked here. And then if you go to the next slide, we have even more links to different value analyses focused on solar and wind and looking at capacity credit. This price drivers report at the bottom shows sort of a longer assessment of over time of how prices have changed and why. And we're always happy to entertain specific requests for data. But I have a couple minutes here. I just want to do a little demo of the tool. So here's what the tool looks like. You can, for example, zoom in. This is negative pricing frequency in 2021. You can change the year. You could also look at average wholesale price, or you might want to look at the highest 100 price hours. Maybe we'll just look at average wholesale price. And say we are interested in prices in PJM here. You can see that there's some missing data for this, but it gives you a time series, and we might look at ISO in England as well. Here we can see how prices have changed over time in real dollars for a specific location. Another feature is we can look at the average wind and utility scale, solar utility scale output for each year, and this is a diurnal cycle, so midnight to midnight, and this is the middle of the day. We can see there's obviously more sun and solar energy generation and during the middle of the day. And we could look, for example, at solar heavy California, and here we see how dominant solar power is in California in terms of total renewable energy. And you can see as you go from older, which are the lighter shades, to darker to 2021, which is the selected year here, you can see that there's been large growth in the renewable energy, and that's affected net load, which you can look at here. You can also look at how that's affected prices. For example, 2021 prices in California were actually sort of on an average level if you're looking historically across many hours of the day. And for example, that's different from, say, if we look at prices in SPP. So first of all, we can see the continual growth of renewable energy generation. This one dominated by wind, so it's nighttime focused and less generation during the day. We see that prices were a bit higher in SPP in 2021 than previous years, and a large cause of that was these extremely high prices in the February cold event. These are not quite as extreme as in ERCOT, but still noticeable nonetheless. So for example, we could look at a seasonal impact, look at fall last year instead of the full year, and you can see that prices are much more similar to the long-term historical average. The orange bar, for example, is more similar to average bars over time. So that's the type of analysis you can do on this tool. There are some other features linking, more directly linking VRE and load to price signals, which I won't go into now. But there is documentation and a summary of some of the main features of the tool and links to other relevant reports on this site. All right, so I will pass it on there.
Well, great. Thanks, Dev. I'm going to take it over here to talk for a few minutes about the interconnection queue data that Berkeley Lab collects and compiles and shares. So I'll give a quick background first. Actually, Berkeley Lab has been collecting interconnection queue data for quite a number of years. Historically, we would just kind of summarize it and put 1 or 2 figures in our annual wind or solar market tracking reports. But more recently, we've been really expanding the data collection and dramatically expanding the analysis of these data. And now we actually release a standardized and cleaned interconnection queue data file annually. So, I mean, part of the reason for that, we're seeing just a lot more interest and urgency around the interconnection queues and the data and what they could tell us. For example, wind and solar project developers have been citing interconnection issues as one of the leading barriers to getting their projects to completion. We have a lot of interest from FERC around interconnection issues. In July of 2021, they released an advanced notice of proposed rulemaking that was designed to study and reform procedures around interconnection. And then just this month, the Department of Energy, the Wind Energy Technologies Office, and the Solar Energy Technologies Office in collaboration launched the Interconnection Innovation Exchange Program, or I2X. That's designed to enable faster, fairer, and simpler interconnection. So this has really become a hot topic, I would say. Next slide. With that background, I wanted to just take a moment to describe what the interconnection queues actually are for those on the call who might not know. So a grid operator basically requires any project seeking to connect to the grid to undergo a series of studies to understand and assess the impact of injecting new electric capacity at a specific location on that grid. And that process is designed to establish any new transmission upgrades, like equipment or reconductoring of the transmission lines that would be needed to connect that new project safely and reliably. But it also assigns the cost of that equipment upgrade. And any projects, wind, solar, storage, gas, that are undergoing those interconnection procedures are basically known to be part of the queue. So those interconnection queues are publicly available and are published by all these different entities that you see shown on the map. We collect interconnection queue data from all of the 7 ISO RTOs in the US, as well as 35 non-ISO utilities and balancing areas. We estimate that those 42 entities for which we collect data represent about 85% of the total US electricity load. We really do our best to collect any data from these queues that are publicly available, and then we clean and standardize those data. The current sample has about 8,000 active projects that are actively seeking interconnection, 12,500 projects that entered the queue at some point but then withdrew, and another 3,500 projects that went through this interconnection process and then went on to become operational projects. I should also note that these data include projects that just connect to the bulk power system or transmission scale resources. So this does not include behind the meter projects. And the data that we have currently is a snapshot as of the end of 2021. Let's go to the next slide. So as I mentioned, this is an annually updated product. In addition to a briefing report that's a PowerPoint style deck, like I said, we also release a cleaned Excel format data set that can be downloaded at the link shown there, emp.lbl.gov/queues. And we also produced, as others have shown earlier today, an interactive data visualization. That's also hosted on the EMP webpage, and there's another link there, but you can also get to it straight from the landing page I mentioned above. And I just will note one thing before I give a demo of the visualization here. Given that this is kind of a solar data focused webinar, it's maybe worth noting that as of 2021, about 65% of the generating capacity we see in these interconnection queues is for solar. And that's about 676 gigawatts of solar capacity in the queues. So let me take it over and do a quick demo here. So what I'm sharing here is just the landing page to the interconnection queue data and report that we have. If you scroll to the bottom, just like on the other ones, you're going to see a tab that says Files, and also another tab for visualizations. So you could click there to see these data visualizations that we've produced. As you get into the data visualization page, you're going to see an introduction page that kind of gives a little bit of background about the data and how they're collected. And I'll just highlight a couple of these tabs that you see across the top, but these are just all different ways to kind of visualize and explore the data. So first, you can look by region. Of course, we have the 7 ISOs highlighted, as well as the Southeast region and the West region. Those represent kind of an amalgamation of a bunch of different individual utilities. You can look at the different capacity makeup of each of those regions. At the top, you can see these bars represent capacity that entered the queue just in the most recent year. And then the lower bars represent the total or cumulative capacity as of the end of that year. Just for the sake of time, maybe I'll just highlight one or two more of these tabs. I think this one is pretty neat. This is a new visualization we created this year showing the existing generating capacity in the United States. That's shown here on the left. In 2010 and in 2021, just the kind of makeup and capacity of different resources that are already connected and providing power to our grid, as well as comparing that to what's in the queues. So again, 2010 and 2021, and remarkably this year, as of the end of 2021, we actually have more capacity in interconnection queues than our total installed fleet of power plants in the US. Last one really quick, just looking at trends in terms of capacity in the queues from 2007 through 2021, you really see just this rapid influx of new capacity in the queues, again, dominated by renewable resources like solar, wind, and storage. So let me pause there and I will pass it along, I think, to Ken to take the next slides here.
Hello, everybody. That's a lot to follow. I'm a professor at Yale, an economist, and I've been having the good fortune to collaborate with LBNL for quite a few years now. And I'm just going to talk for a couple minutes to give you just a little snippet of insights that have emerged from some of these academic collaborations, and hopefully give you a sense about how these academic collaborations can go about. There's been a series of papers along the way that have explored the rooftop solar market that I've worked on with folks at LBNL. One that is right here is in the Energy Journal. It was on deconstructing solar photovoltaic pricing from some number of years ago, because we've been working now for quite some time. And this is a project that very much exploited the Tracking the Sun database that Naeem had mentioned at the beginning, and you'll see he was a co-author here. And it was, other academics, Greg Nemeth and Varun Rai were also in there, and others from LBNL like Ryan and Weiser and Galen Barbos. But we kind of noted that the installed price per watt has huge variability. And one question that arose was why? What is that variability coming from? So that work was to really break apart, is it the pricing? Is it local labor costs? Is it from installer experience? Is it from installer density? And we found that installer density does actually lower the prices. There is with a lot of dense number of installers tend to have lower prices. That tells us something about the level of competition. We did a bunch of tests for search costs and other economic theories to help explain some of our findings there. And we also noted that regions with relatively generous financial incentives for solar were also associated with higher prices, even above and beyond the local labor costs that you might have expected. So this is a fun project because it not only leveraged the Tracking the Sun database, but it also allowed us to bring in, through research assistance, a whole set of other database sets kind of at will. And this is something that it's just a fabulous collaboration. Next slide, please. Following that one, there've been a series of additional papers. So that paper was kind of one of the first ones that I'd worked on with this group. And I should note that was funded by the US Department of Energy quite early on. And several other papers came out of that line of work. But more recently, we've followed on further in exploring the data and trying to understand, using these rich aggregated data, what can we learn about the variability of pricing, and then what can we learn when you're thinking about other aspects of pricing when you say are adopting both solar and now battery storage, which is coming about. So in one of the projects that we have underway right now asks what explains the variability of solar prices even within a geography or within an installer. And what we see here on the left, and I should note these are preliminary results, these slides here, but they give you just kind of a taste. I mean, I think these are just from the raw data, so that there's no way they can be wrong. And would be happy to follow up, but we can look at the coefficient of variation, which is, if you're not familiar, the standard deviation divided by the mean, and it's a common way of understanding variability. So the coefficient of variation of solar prices between installers or within installers. And you actually see, so even within an installer, so you have a given installer, they have quite a lot of variation in their pricing as well as between installers. And so this is kind of what we said. We also saw kind of an upward trend, which was quite interesting. Another question, you can go to the next bullet point, that we've been looking at is, what are the factors that explain the co-adoption of solar and energy storage? So as we see energy storage battery prices really dropping, we've seen a real uptick of adoption of energy storage. And we've been examining, when does this happen? Why does this happen? And one of the very interesting things we've seen is that co-adoption is kind of a dominant force here. You do have a bunch of people who have battery and solar that previously adopted, but co-adoption is a really dominant force, and almost nobody, very, very, very few, have standalone batteries without a solar system. So what I hope you can take from this is just that the folks that you've just heard from are fantastic to work from. Besides being amazing data aggregators, they also bring quite a lot of intellectual capital to bear. And as an academic, it's been a lot of fun to work with them and take advantage of these data sets.
Thank you so much, Ken, for that and for the nice words. So we walked through each of these main data sets that we develop and use in our DOE-funded work. And Ken shared an example of how this data has been used in our collaborations. So we obviously have a little bit of time for some questions. A number of questions already have been answered live. But know that you can always kind of reach out to any of us here. Our contact information is listed. We are, always available to answer questions about the data, how to access it, etc. So again, please enter your questions in the Q&A button, or just click on the Q&A icon in Zoom, and we can kind of, for the next 6 minutes or so, walk through some of these. So let me go ahead and look at some of these. So I noticed that some states are not listed in the drop-down menu. This was for the Tracking the Sun tool. Is data for those states not included? So yeah, that's right. Not all states are covered by Tracking the Sun. We have coverage for just above 30 states, I believe, for Tracking the Sun. In other cases, we do have information in the report, but we can't share it publicly in any way because our data agreements don't allow us to do so. So what is there is what's available. Great. So do any of these resources have an API which can be pinged to get new data as it becomes available, even if that's annually, to update local models that other researchers may be developing? So I can answer that. I don't believe, and if someone on the line would like to correct me, please do, but I don't believe that any of our data is available through APIs. We have thought about it, but because it's kind of an annual update, we've decided to just kind of make it downloadable on our website. We try and keep the header names the same whenever possible. We do have kind of data dictionaries in some cases that kind of explain each of the variables. But if there was sufficient interest, that is definitely something that we've thought about in the past. So keep your eyes out for any updates on that. Is anyone else on the line?
Hey, Naeem,
Yeah.
just really quick, this is not a data source that we presented on today, but the US wind turbine database, which obviously is focused on wind energy, not solar, is updated quarterly and does have an API. So if anyone on the call is interested in the build out of utility scale wind turbines in the United States, those data are available publicly via an API and also via typical kind of tabular downloads like CSV.
Great, yeah, thanks for that, Joe. And again, definitely this is something that could come up in the future. It depends on kind of if there are a number of requests. So thanks for at least providing that feedback. A number of the questions have been answered already. So please, when you go to Q&A, I think you can click on answer to see some of those. A lot of the ones that haven't been answered are those that are maybe directed towards me for tracking the sun or the demographics. With the increased focus on energy equity, could you point to a specific solar equity data set that can be used to demonstrate progress in equitable energy development, adoption, or access? So here, I think the best way to gauge, well, one of the ways to gauge progress is kind of incomes of solar adopters and how those may have changed over time and changed from one geography to the next. And for that, the solar demographics tool that I had alluded to or presented shortly in my section is a great way to kind of gauge that. In the report itself, so in the slides themselves, there is more information than is available in the tool. So we do, and we will in the next upcoming version of the report, have information on race, for example, and other demographic information. So definitely the tool is a great place to start. You can download the tract level data. Also could be useful for this. If you have any specific questions, please feel free to email me. All right, one other question on LMI households. So solar installation data for LMI households, do you capture actual installed capacity or just the count of households? So we do have, since we use tracking the sun data, we do try and include installed capacity when we can. Some of the data sources we use don't include kilowatts in that's sometimes in permitting data. So it's not as complete as kind of the count. But if you are interested in installed capacity, we can definitely share that, understanding that it's not a complete data set. All right, so with that, it's approaching the top or bottom of the hour. I hope this has been informative for you all. I'd like to thank my colleagues at the lab, as well as Ken Gillingham for presenting today. And again, this will be posted online. So please, if you'd like to share it with colleagues, you can go to emp.lbl.gov, click on webinars, and it'll be posted online there. Have a great rest of your day, and goodbye.